starts at 0. One full wave of a sine function starts at 0, ends where? 2 pi. Then halfway through, it gets to pi. Highest point's 1, lowest point's negative 1. That's the standard stuff, right? The good news is, while that's encouraged that you know that, if you don't, it's not the end of the world. You go into your calculator, type in the y equals menu, sine of x, and do a quick zoom trig and see what's going on. You can still get the shape, the structure of a sine wave. Because, oftentimes, something slips through the crack, you forget little things. All right? So what I need is the area, because you got to think, the net area between pi and 2 pi. Well, if I have the picture in front of me, then I have what I need. So I'm looking for the area between pi and 2 pi. That's this guy right here. They told me that going from 0 to pi itself is valued at 2. This guy over here is worth 2. So what's this one worth? Negative 2. It's the same area just below the axis, right? Right, so while you could have typed in math 9, pi to 2 pi, and so on, just having a good sense of what a sine wave looks like actually gets you a good chunk of these answers. So going from 0 to 2 pi, what do we get? 0, because we gain 2. Yeah, it's symmetric. Equal parts positive and negative. We gain 2, and then we lose 2. So it's a zero-sum game. All right, pi over 2 is halfway between 0 and pi. So let me get that 2 out of there. We know that the entire interval is worth 2 units. If I chop it in half, what do you think each part is? Each part's going to be valued at 1. All right, so each half arch, if you want, is going to be worth 1 unit. So going from 0 to pi over 2 is going to be 1. So since we know a cosine function, we're not there yet, but we know a cosine function is just a horizontally shifted sine function. It's going to have the same areas, just in different places. So we now know that each arch in a sine wave or a cosine wave is valued at 2 units. Right? So each half arch is 1 unit, and off to the races. So now you can pretty much analyze anything. Right? Some of them are a little easier than others, though, because in D, you have a sum that's telling us that we can break up the integral, go from 0 to pi for the function 2, and then go from 0 to pi for the function sine of x. Asked and answered. 0 to pi, they gave that to us, that's 2. Let's see if we pick this up. Going from 0 to pi, if I want to find the antiderivative of 2, what is that area going to be? 2 pi. Right? Because this is a horizontal line, 2 gives you a horizontal line. And then it's going to start at 0, end at pi. It's going to create a rectangular region. Base pi, height 2. 2 times pi. The shortcut, talked about this on the previous page, is that you just take the difference between the boundaries of integration and multiply by the integrand, what they call that. 2 pi plus 2, leave it at that. There's no need to simplify. There's no way to simplify. I mean, you could factor out a 2 if you want, but to what end? I mean, if there was a variable in there, sure, but it's a number. So 2 pi plus 2 is where it's at. Constant multiple, pull it out. Some of these, it would take longer to actually type it into the calculator than it would be to actually figure it out. So 0 to pi of sine x, we've done this like 4 times already. 2 times 2 is, you guessed it, 4. So some are easy, some are hard. Some are really hard. Some are really easy. Like F, if you're doing it by hand, when I show you, it'll be like, oh, that's not that bad. But at first glance, it looks really hard. G, on the other hand, is actually really easy. And then the other ones kind of fall into their own categories. So let's tackle F. This is saying go from 2 to pi plus 2. All right. So let me do a quick rough sketch of just a regular sine function, going from 0 to 2 pi. So one full sine wave. I know I don't have to go out as far as 2 pi, but I want to. All right. So what this is telling me to do is find the area bounded between 2 and pi plus 2. So 2, I'm just ballparking it, would be like right here. Pi plus 2 would be like right here. Roughly. Because I know that pi is 3.14, so I just want to get closer to the pi. So I need the area between these two guys. But not of this function. This is like the sine of x. I need y of sine x minus 2. Y equals sine x minus 2. Right? So what is sine of x minus 2? What does the x minus 2 tell us to do to the sine function? Say it again? Not break it up. If it were sine of x minus sine of 2, then you could break it up. But because of subtraction within, it's a different story. Shift it to the right by 2 units. Shift sine right 2 units. All right. So something that was really funky to look at just got a whole lot easier because they told me to find the area between this guy and this guy, but they're telling me to shift the sine wave itself over 2 units. So this point, I don't want to do that either. I'll do them. This point here goes to this guy. This point goes to this one. The maxes are going to move over. And you're looking at something like this. You could continue on if you want, but all that extra stuff is irrelevant. Right? So I need this area here, which is one complete arch of a sine wave. And what do we know the area is contained within one complete arch of a sine wave? 2. So once you realize visually what's going on, you got it, right? Now, again, this is to develop a deeper understanding. I could just type this into my calculator in radian mode and move on. I get the answer. You really, yeah, I mean, it's kind of hit or miss as a teacher. I look at your work, I see you have the right answer. For a question like this, I don't know that you know why that's the answer. I know you can get the right answer, and that's wonderful. But having a visual sense really makes a big difference. And again, if you're, I mean, it may not even be your fault. Like if you took pre-calc, for example, where you usually learn about trig graphs, and it was one of those semesters where it's like snow day after snow day, and the teacher's like, well, I got to cut out a topic, so yeah, before you get to calc, make sure you teach yourself trig graphs. It's probably going to be pretty important. Then you may not have got a pretty complete view or understanding of this stuff. But yeah, if you practice with this, it's not going to do you wrong. So I mean, if you really need the help with trig graphs, then go to my YouTube channel. I mean, you can go to me too, but I'm operating under the assumption that you don't want to. You know, like you want to do this in the privacy of your own home or in the car or something, or on the bus or whatever. then yeah, go to TCAN 290, type in trig graphs, and see what I got. Right? It's basically creating these graphs both by hand and using the calculator. And of course, click on that thumbs up icon. And yeah. Hey, I got a notification, 500 subscribers. All right, you don't care. It's fine. Oh, thank you. Thank you. So one person's going to pass, everybody else does. So for G, we have sine of u du. And it's like, oh, we didn't learn about u substitution yet. It's not really relevant because this could easily be sine of x dx. It's a change of variable. It could be sine y dy. It doesn't really matter as long as the argument and your d whatever are consistent. Okay? So I can draw any sine wave, propagate that bad boy. Just get an axis in here. And let me call this location 0. It's just asking me if I have symmetrical bounds in a sine wave, what's my area going to be? So let me create symmetrical bounds. I'll call this one negative a, and then using the same distance, go out to positive a. Negative pi to pi, negative 20 to 20, it doesn't matter as long as they're symmetrical. In a sine wave, if you have symmetrical bounds, you can see here, I have 2 negative parts and 2 positive parts. Each negative part is going to cancel out with each positive part. That extra stuff is irrelevant. It's going to go to 0. All right, so knowing the nature of graphs is helpful because if I had something like, same question with a cosine graph, then it's a different story because cosine functions are not odd functions, they're even functions. So whatever area you would get on an interval, you would double it if it's symmetric about the y-axis. All right. For h, again, something you can do on the calculator. But, assuming you don't want to, you'd look at what this graph is really talking about. Sine, I'll write it as 1/2 x. This is telling me that I'm only going to get 1/2 of a sine wave in the 2 pi interval. All right, so graphically, if I were to go to 2 pi, I'm only going to get half of a sine wave, still the same amplitude. So instead of 1 full cycle, it's half a cycle. So something like that. All right, so same max height, but the width is double. It's double that of a single arch. All right, so if I know that a single arch of a sine wave has an area of 2, it's going to be 4. Yeah. Because I'm only changing one parameter. The constraint on the vertical end is not changing. So I'm not gaining any height, but I'm doubling the width. So you just think about a rectangle. You have a rectangle with a given area. Double one dimension, you double the area. Double both dimensions, then you're doubling and doubling again the area. So you're going to raise it to the power of 2. Then we do the same thing with a cosine graph. So it's like start all over again, draw a cosine wave. Not really. Yes and no. I'll do the roughest of sketches on a cosine graph. 0. This is my pi over 2. Here's pi. 3 pi over 2, and then we end at 2 pi. So you just need a sense. If I'm going from 0 to pi in this cosine graph, I'm looking at this interval and this interval. What do I get? Get 0, yeah. All right, because while the cosine function is not symmetric about the origin, so it's not an odd function itself, on this particular interval, you have equal parts positive and negative areas. So when you add them together, they're going to zero sum. They're going to cancel each other out. I don't really like number 5, so I mean it's easy enough to do. You know what? I'll put a star on it. You could try it if you want. I'll give you the answer next class, but I don't like it. I never have. It was just from an old textbook, and I felt the need to include it. You know what? I'm also going to put a star on number 4, just because I'd like you to try to wiggle your way through that one first before I give you the answer. So to speak.